Hello, everybody. My name is Kevin Kocek. I'm the founder CEO of Chemical Q Device. Here for Thursday, August 1st, this is 2024 for 146. And this is about total synthesis guidance for chemists using large language models and large multimodal models prompts. So I'll be covering these two papers. So it's basically uploading these papers with the supplement, if it's peer review, supplementary information, and asking it questions through this advanced forms of AI. Natural language processing. So an introduction with this is that total synthesis refers to the process of constructing a complex organic molecule, often with biological activity for simpler, commercially available, or naturally occurring starting materials in the fewest steps possible with high yield. Now, two recent synthetic chemistry papers, and this is the JAX paper, Journal of ACS, or American Chemical Society, and Nature Communications were analyzed with LLMMs so that a chemist can more easily reproduce or make the desired compounds more pure, faster, or less expensive in their own lab. Each paper was read manually, along with corresponding supplementary and peer review documents. Prompts with keys were created for LMMs that asked specific information beyond what was provided by the authors to potentially increase the yield of products, in addition to locating exactly where the information was found that supported its conclusion. And the large multi-model or fine-tuned models were tested on 3 prompts per paper and included ChatGPT 4.0, Organic Chem Scholar, Chemistry Chem, Scholar GPT, and Scholar AI. Llama 3.1, 405 billion parameter model, and Nematron 4, 340 billion parameter large language models were also used to generate responses regarding how to make the total synthesis supplementary methods faster or less expensive than used in the original papers, and were judged by a company called Cohere, another large language model. So this is for the first part here. So this is aimed towards, you find reactions in these papers, and a lot of them might have low yield. So I tend to focus on those. And the results basically is the Scholar GPT, which is it's a fine-tuned version of some ChatGPT variant. It tended to have the best across all of the different conditions, and I'll get to the conditions in a second here. And then ChatGPT 4.0 was number 2, and then we see Scholar AI. And unfortunately, the two chemistry models did the worst based on my prompts, right? So that doesn't mean that they're not good at chemistry. It just means that the specific things that I was asking for, other models tended to do better with that. So now the condition 2 was basically, can it provide the correct document and page number of the text selection that it's basing its response off of? So only one of these models did well, the Scholar GPT. And again, I mentioned that before, it's the #1 model across all the different conditions. And you see Chemistry Chem and Organic Chem having one instance apiece, but the Scholar GPT more consistently, 4 of the 6 prompts, it did well. And we see this for condition 5 is basically, this is a more advanced question. So this is basically saying you understood the context. Now, how specific can you get in generating a response that would have the potential of improving the percent conversion or the yield or the EE, percent EE, these types of things. And ChatGPT 4.0 did the best with that. So, I look for specific types of reagents to use, as opposed to it just saying generally, check the temperature, check the, your TLC plates. A lot of times it'll give specific reagents for this. And here's the scoring thing. So for section A, and again, this is more focusing on if there's a low yield in a specific reaction. So the first condition, it provides correct generation context regarding attached documents. So the prompt goes in the bubble, that you type in, and then you use a paperclip feature with any of these models within the ChatGPT interface. Number 2 also provides the correct document and page number. That was the hardest, except for Scholar GPT. It got 4 of the 6 prompts, and it was able to do that. And condition 3 also provides the correct selection of text. Usually the models did well with this. So this is basically saying there are selections of text that are influencing the AI's decision to provide a recommendation, either if it was general or it gave a more specific recommendation for a different type of reagents to use. So condition 4 also provides general reaction substitution details to the paper. So this is, basically saying like, make sure to do the very general tasks, that you might forget about when you're in lab, but not giving like a specific, use this specific compound in this, so use this specific method. And condition 5 was basically that, you have a specific, a different type of reaction that the AI model is recommending over the original paper. So 10 out of 10 is all 5 conditions met. It was actually done once by the organic chemistry model, but there was a lot of 9.5s, which is 4 conditions, 9.0s, which is 3, 8.5, which is 2, and then 8.0, which is 1, or 6.0, no conditions, meaning that it didn't really pick up on the context of the paper. And then, so what we see here, this is the JAX paper. So there was 2 papers that were reviewed and further analyzed with AI. And this is the convergent and efficient total synthesis of helinone enabled by CH functionalizations by Jin et al. And again, this is a 2024 Journal of American Chemical Society paper. Okay, so we see it's the 36, and the prompt was what substitute reaction beyond what is mentioned in the paper should be used to convert 36, the starting material in this specific reaction, to 37, this one here at 45%, in higher purity, meaning that this percent needs to go high or higher. So you see all of these did pretty well, 3 9.5s, a 9.0, and 8.5. And with the Chat GPT, which I included here, and again, it tended to have the best of this condition 5 response, even though it never got the correct document and page number correct, but something like the Scholar GPT did, usually that it got. Okay, so again, it's bound by those conditions, and the excerpt for this, and the generations or the outputs get much longer than this. To improve the purity of the conversion from 36 to 37, again, this is all the AI response right now. You should also consider using a more controlled and mild oxidation reaction, employing Des-Martin pyridinane, DMP, or pyridinium chromate, PCC. These reactions are known for their mild and selective oxidation properties, which could help in achieving a higher purity of compound 7. So you can see this reaction is deep inside a supplementary paper, right? This is, I think in this case, like 80 pages. And in addition to the original paper, which is shorter. So it's looking through all this information and basically the question or the prompt that I had found that this specific location was the information that it needed to provide additional recommendations. Okay, so then it actually goes on, and in this case, my condition 3, which is provides the correct selection of text, it also did. And then here's the kind of like the recontext version in the provided documents, the current method. And then you'll see the Na2 eosin Y under 456 nanometer light is up here. Okay, so this is all AI, reading the paper, yielding compound 37, which is, it says 45%. This says 45% purity. Okay, so you see that it is highly specific with these, reactions, as far as like, this is challenging tasks, say, for if you were just the first time reading the paper, how long would it take for you to read this JAX paper in the supplementary? This is happening in the matter of seconds. And we see that the performance is high, right? There's always room for growth. And I'd say more specific, to say like, oh, okay, well, I noticed on this specific 36 that it has this, functional group over here. So instead, I'm going to use this specific reagent that would do better with it. It hasn't reached that level that I've seen, but it's still providing very specific details in regards to the reactant to get to, potential better purity. And then this is another example here. So I chose prompt 4. So this is from the Nature Communications paper, collective total synthesis of stereoisomeric yohimbine alkaloids. Alkaloids is just, it has to have at least one nitrogen here. And then, so this was done by Tang et al. So this was accepted in 2024, Nature Communications, using these reagents, iodine, and then this phenyl silohydrogen and dichloroethane to reach this, okay? So I asked it what substitute reaction beyond what is mentioned in the papers, and in this case, there's 3. There's the main paper I attached. I also attached the supplementary, and I also attached the third, which is peer review. Very interesting. Like this is kind of like you have to change this in order to get the paper accepted. 3 peer reviewers. And yes, occasionally it did pull information from peer review in a matter of seconds, right? So at the bare minimum, with all these tools, you have to be using AI, I'd say, to keep up as at least a checker, right? To say check specific things. And then the next step is obviously to give you recommendations. And then further down the road, I think we're going to see, mass adoption, that it's going to take significant amount of the work load. And then, so you see here, this was a harder question to answer. So I actually didn't give a yes for condition 4 or condition 5, which meant it didn't provide a general reaction. It didn't provide a specific one. And the one I chose to include here was the Scholar GPT. And this one had the highest score out of this bunch. So it was able to return, the correct generation context, like it knew what it was doing. And then number 2, the correct document and page number. So you see the page 4, and then of the collective total, whatever, this is from the main paper that it's getting it from. So again, it was the only one out of the 5 that would correctly do it for most of the prompts of generating that page with the document, that I had uploaded. And then condition 3, the correct selection of text. So the exact excerpt that I chose to include here, here's the relevant text from the document among several Lewis acids, trimethyl iodide. So this specific statement here, I can copy and paste into my find feature in the original paper to verify that this is coming from that specific spot. And then I also verify the page as well. So page 4 of this specific thing. So these have to be done manually, especially right now. And of course, as we trust AI and AI more, we'll always, especially for very key things, want like a human checker and also another AI checker too, to keep things in line, right? But right now, it's the speed that's really paying off. And if you're not using AI at this stage, which is very readily available software, then, you're probably not going to be ahead. So here's the second section here with speed and cost. So I took these same 2 papers, and instead of focusing on the full papers and supplementary, I chose, or peer reviews, I chose very specific, the supplementary methods in both papers. And I gave it the task of basically saying, you need to be able to look at this and update it. So if there's anything that you can think of with the AI should be able to tell and provide information. So the 2 prompts were basically this, is the supplementary methods in both, revise these methods to increase the speed of a 2024 total synthesis published in a top chemistry journal, or decrease the cost of the same thing. And I included the 2024 and top chemistry journal just to mean that like it should try its hardest. This isn't some old paper. These are new methods that the researchers are using. And it's a desirable thing to do a lot better than the current supplementary methods in both of these 2024 papers. So this was given to Meta, so Llama 3.1, 405 billion, which just came out last week, and then NVIDIA, Nematron for 340 billion, which is a really good model, and it's actually proved to be better than some of my other models that I've been testing on. And then I gave these responses to Cohere, which is another large language model, for it to determine basically how much better Meta or NVIDIA's LLMs are compared to the original methods. Okay. So here's an example of this is a generation here. This is an answer from Llama 3.14 billion model of the JAX paper. And I said, revise these methods to increase the speed of this. And I didn't tell what the paper was. I just pasted in the exact excerpt, from the supplementary. And I told it that it needs to be competitive, right? This is a 2024 paper in a top chemistry journal. So the thing that I like about this specific response is that automatic, purification, it gave specifics. So I've actually used the Waters auto purification system. It also said the biotage as well. And reaction monitoring as well, the React IR and Raman spectroscopy. These actually show up in the judge's response, and they say it's good that the Llama 3.1 model specified these because these weren't used in the original paper, right? So all these things will get more specific as time goes on and prompts get better and models get better. But this shows very specific details. And I like with the NMR, it said the 900 megahertz or gigahertz. When I was in chemistry, in graduate school, 2012 masters and some after that, a 600 megahertz was a little bit harder to come by, and anything bigger than that, I think the sizes are still prohibitive at 900. But regardless, if you're running at that high field, it should reduce acquisition times. So I really like that answer right there. Most organic chemists can tell you that too. But again, it's specific. And other ones tell you use the specific Bruker, 600 megahertz as far as the generations from AI. Now, the fast NMR techniques, the so fast HMQC, I've used HSQC. I haven't used this, like mentioned here, ASAP, which is, I think, proton-proton coupling. And, so we see some other specifics, which was good. So again, this is Llama's 3.1, the 405 billion, which just came out. It's its response to, these suggesting, and some of these other things, they're just not as specific, but they're, flow chemistry, explore the use of flow chemistry techniques, these types of things that you can gloss over that may be available to you or your lab. And it's just, it's good to see. So this next specific one is the judge of the previous slide's response. So I said on an overall scale of 1 to 10 in 0.1 increments, with 10 being the best score, rank these new methods in detail based on their ability to increase the speed of the original paper published in a 2024 top chemistry journal. Okay, so in other words, do your best. And again, so it goes through its, 9.0s, 8.5s. Now the Cohere one, the scores tend to be pretty equilibrated, like about 8.5, 8.7. And I think that, the question was a little bit less specific, and I can't really knock it down that much. But here we see the React IR and Raman spectroscopy. These are not mentioned in the JAX paper. So it means that it's really taking a lot of these things we see here, mentioned from Llama 3. It's dealing with all of this context. So the judge has to look at the original paper, a block of text I gave it, and I also gave it a block of text from the Llama response. And then this was the prompt to differentiate those two and basically say, how well did Llama do in improving some of these methods from the original paper? Okay, so, and these can get quite lengthy, but it's important to see the types of generations that you're getting and how they're able to solve new problems. And I would say a lot of times it's just really good advice, like it's a recommendation, like a really good recommendation as far as don't forget to do this, don't forget to clean that, don't forget to, use the purest solvents and, get the oxygen out or, by degassing, those types of things. So here are the conclusions. The prompts required specificity to yield general or specific reaction substitutions such as beyond what is mentioned in the papers that was required. Not all low yield reactions were investigated using AI. I included 3 prompts. It's in the report I have online. So there's 3 prompts for each paper. And then for each prompt, there's 5 models on the first section. Now, condition 2 was a limitation due to not citing both the document and the page number with the text they were cited. except for, of course, the Scholar GPT, which was at about 67% for that one. Further verifications regarding the validity of specific reaction substitutions are also needed. And additional work is also required to improve the model's ability to provide specific reactions for complex molecules. So really going atom by atom, I think is really needed at this stage, and saying like, okay, or at least functional groups. This has this functional group. It's not compatible with this, set of reactions, those types of things. Okay. And then condition 5, which was my hardest, I said it had to be specific reagents, but then it's going to keep going into like, PhD level, postdoc level, these types of things, as far as saying, push a button, look at this paper, and then the output, these recommendations, like how much does it help? We know it's time. It's definitely worth running, right? Because it's so much faster than reading papers and reading supplementaries and, these types of things. So the methods mentioned in this guidance allow for significantly faster results for new reaction recommendations than what humans can perform alone. And greater AI reliance for synthesis will follow as yield, speed, and cost consistently improve as new models are released. So a lot of these things are dependent on the models that are used. So when I say Chat GPT 4.0, or if I say Llama 3.1, 4 or 5 billion, there's always little tools you can adjust. You can actually fine tune on additional data, so if it's the Llama 3.1 405B, that's going to be a little bit more challenging to fine tune on a private, your own GPUs, like many GPUs. And then if you want to go the whole way and then retrain the whole thing, based on its architecture, you're talking, they use 16,000 GPUs. And then this is like, you probably need hundreds to, it just depends on what you're trying to do. But the moral of the story is these models just keep coming out. And it's like every 2 or 3 weeks, it's like, there was Llama Week that we just had. And then, ChatGPT just announced a very cost efficient and faster mini, GPT 4.0 mini. And, these are the types of things, and it's important to test on your own data because, is that important to you to have a document and the page number for each specific reaction? I think it is, but obviously a copy of the text that it's selected, that is probably more important, right? If you have that text selection and you just copy it and then paste it into the find of the document to check that it was correct, that's very powerful, right? So some of these other things maybe, more so it's just nice, because you're just at glance, because you can instead of going to find, now you can go directly to the page number and then hit find, right? So these types of things. And obviously the emphasis, I believe, in all these models is more so, on reasoning and, comprehension and dealing with many contexts all at the same time. It's really quite amazing the amount of data that it can look at. And, this report basically shows that at a high level of generating, either a general or a very specific reaction substitution. Awesome. So that was it so this is Thursday, August 1st, 2024. This has been for total synthesis guidance for chemists using large language models or large multimodal models. Discussion 146. My name is Kevin Kocak. I'm the founder CEO of Chemical Q Device. And again, if you need additional detail with this, the report goes through it in more detail, and then expect to hear a lot more as far as, improving a lot of this as well too. Thanks, everybody.